Hi everybody, we're going to be talking about multiplicity in proton NMR in this video. So this is really defining the peak shape. Okay, so a lot of the peaks that I've kind of been using as examples, some of them I've been drawing out specific shapes, and some of them I've just been drawing out that shape. But the peaks, depending on the different environments around them, can split or couple with neighboring protons. So those other words, multiplicity, splitting, coupling, they're all going to be kind of in that same multiplicity realm. Um, and then show up as different peak shapes on our proton NMRs. Just proton, not carbon. We're not going to see splitting in carbon. Okay, so if we're looking again at our general rundown of our proton NMR summary here, the multiplicity that we're looking at is the letter in there. Okay, that is going to be our multiplicity. And that's telling us what the shape of the peak is. Okay, so this is a quartet, that would be a singlet, that is a triplet. And we'll go through what each of those look like, obviously. So splitting happens when you have nearby non-equivalent protons impacting the magnetic field of the peak that you're looking at. Okay, so in this case, the peak that shows up at 4.12 is a quartet integrating to 2. So this tells you about the chemical environment of that peak. This tells you about the number of protons around it, and this tells you how many protons actually are part of that environment. So it is a little bit much in terms of information, so just kind of keep that in mind and then keep practicing as usual. But it's really looking at kind of nearby protons acting as little magnets and changing the direction of the magnet of the little proton that you're looking at. So splitting is generally observed in protons that are 2 to 3 sigma bonds away from each other. So in a situation like this would be 1 sigma bond, 2 sigma bonds. The most common you're going to see is the 1, 2, 3, okay, where we're seeing three sigma bonds in between our coupling or splitting protons. And this is when H and B are not equivalent. So I have these two H and B on the same carbon. It can happen. We're gonna see a few instances where that's the case. But just because it's a CH2 does not necessarily mean they're going to be in the same environment if you don't have that mirror plane reflecting them in each other. Okay. So when A and B are not equivalent, that's when we're looking at splitting happening. The most common one is going to be this three bond coupling though, where you have some two different environments and they are coupling with each other. So in this case, HA will couple with HB and HB will couple with HA. So you will see the effect of the opposite or the neighboring protons in all of the peaks that you have. Okay. So it's something to keep in mind is just as a double check that if you've got something that just does not make sense and it doesn't have what looks to be like a coupling partner, something probably went wrong in the analysis. But very, very important, splitting between equivalent protons does not happen. So again, all of this really comes back and stems down from being able to identify those equivalent protons in carbon environments. So if you're not feeling good about that, keep practicing that, keep asking questions. It is probably the most important part of this whole NMR business. Okay, so if we're looking at neighboring protons, we really need to be thinking about how many neighboring protons are present because that is going to tell us what's happening with the multiplicity. Okay, so a neighboring proton, we're looking at protons or H's on adjacent carbon atoms to the one that you're analyzing. Okay, so if we are looking at these two H's, we want to be thinking about how many neighboring protons we have. So we're looking at our adjacent carbon atom, and I'm just going to draw in those H's. Okay, these are going to be our neighbors. Okay, so we have 3 neighboring protons to our A environment. Okay, so the protons in the A environment is going to have 3 neighbors. Okay, if you're looking at it from the perspective of this H, it would be neighbors with the A proton, so 2 there. And you would also have all 6 of the protons in the 2-methyl groups that are also neighboring it. So when you're looking, you want to make sure that you're not just looking one way. We want to be looking both directions and collecting all of those neighboring protons all together. And again, this is an example of that 1, 2, 3. Sigma bond splitting or coupling to help us find those neighboring protons. So this would have 3 neighbors to our A protons. Okay. And keeping in mind that if these 2 H's are equivalent, they will not be splitting each other because we don't split equivalent protons. So if these 2 have that mirror plane, which in this case they do have a mirror plane reflecting each other, these are equivalent, so they do not count in that neighboring count. We're just looking at them all together as one unit. Okay. So when we're finding our multiplicity or our peak shape, it is going to be our number of neighbors plus 1. Okay, this is often referred to as the n+1 rule, and that's what's going to give us the actual shape of our peaks. And this all comes down to statistics and kind of the having your little proton magnets either aligned or misaligned, and what the statistical likelihood of either of those various mixtures happening. So that's what's leading us to these very kind of particular peak heights that we're seeing here. So the peak heights are important. And I say that just so that you don't look at this and start to think that anything that has just 3 tips on it is a triplet. It is not, okay? A doublet is specifically a 1-to-1 like peak height of those two peaks. A triplet is going to be a 1-to-2-to-1. A quartet is a 1-to-3-to-3-to-1, okay? And that's all coming down to just how many possible iterations of various aligned and misaligned you have. I recommend looking at the textbook if you want to see that. I'm not going to ask too much or anything about that idea. But just to keep in mind that a triplet is not a real triplet if it's like that. Like that would not be considered a triplet because it doesn't have that really distinctive peak height and shape to it. So when we have 0 neighbors, we've got the n+1 rule giving us a single peak. So a single tip to that peak. And that is a singlet, which is abbreviated as S. 1 + 1 is going to be 2. And so we're going to have 2 little tips on that doublet. And it's D. Triplet is 2 + 1. So we're at 3. So now I've got 3 little tips. Or you can think of them as 3 like local maxima. Those 3 little tips, again, 1-to-2-to-1, and that's going to be abbreviated as T for triplet. 3 neighbors is going to be a quartet. 4 neighbors is going to be a quintet. And you can see this happening with many, many more. But these are going to be kind of the common ones that you see. If you end up with something or see something that's just labeled M for multiplet, that's typically used in a case where you're getting a lot of peak overlap. And so the splitting is obscured. So something like that might be shown as just a multiplet because it's not really clear what it is. There's definitely some obscuring going on here. It's not a clean doublet, triplet, any of those types of things. So overlapping peaks, they will frequently be labeled as multiplets. Sometimes you can kind of tease it out, but it very much depends. Okay, so let's look at an example here, just so that we can kind of put a little bit of reality down in this. So we're kind of looking at a little bit of a combination here where we've got multiplicity, we've also got integration, and the H environment, I'm just going to label it as letters for now. So we really have H's here. Those three will all be the same. We've got H's here, there, go one there. Okay, so if I'm looking at my equivalent environments, I've got all of my A protons there, B, C, the two methyls, I'm going to call them D, and we do have that plane of symmetry relating the two methyls on D. And then we've got our E over there in the middle between the two methyls. So that's the development of kind of our isobutyl group there. Okay, so I'm going to look at A, B, C, D, and E. Okay, so for A, okay, if I'm looking at the protons on A, all of these protons are A protons, so I'm not getting any splitting or any neighbors from them. But what I am getting neighbors from is this carbon right here, which has two hydrogens on it. So it's got two neighbors. So then I've got 2 plus 1 is going to equal 3. So this is going to be a triplet. Okay. For B, again, these two H's are in identical environments. They are equivalent. So they are not getting any splitting from each other, but we are getting splitting from the two carbons next to it. This carbon doesn't have any protons on it, so no splitting or no neighboring from that. But that carbon does have the 3 protons on it. So that's going to be 3 neighbors. So 3 plus 1 is going to equal 4. And that's going to be our quartet. Okay. For C, I'm looking at those 2 protons. And again, that neighboring carbon doesn't have protons, so no neighbors there. This neighboring carbon has 1 H on it. So I'm going to get 1 neighbor. That's going to be my E proton. So 1 plus 1 is going to equal 2, and that's going to be a doublet. Okay, D. If we're looking at D, whenever we have kind of the same environments, but they're in separate spaces, we only need to look at the perspective from one of those spaces. Okay, so for instance, I do have the 6 H's in my D environment, but we really only need to look at kind of one of those to see what our neighboring situation is like, because they should be identical and we're not going to count it twice. Okay, so our D environment, we're going to be looking at this carbon right here. And same thing, if you did this one, you'd be looking at that carbon right there. So on our neighboring carbon, we only have the 1 proton. Okay, so D is going to have 1 proton as its neighbor. So it's going to be another 1 plus 1 is 2, giving us another doublet. Okay, then if we get down to E, so E, we want to be looking at all of the possible neighbors that it's got, and we only have the 1 perspective, right? It's just the 1 H for E, so I'm going to be looking at all of them. So if I'm looking at this carbon, for my adjacent carbons, I've got this one, and this one. So I've got 3 there, another 3 there, and another 2. So I have a total of 8 neighboring protons here. 8 plus 1 is going to be 9. So I'm looking at a nonette here. Okay, and that's what we're kind of thinking about when we start to see a lot more splitting. And I'm going to try to count this very carefully to make sure that I actually have 9. 1, 2, 3. I didn't do it even. Okay, so we'd be ending up with something like that where you see a lot of splitting because we've got a lot of neighbors. Okay, if we follow up with the integration on all of these, I have 3 protons in my A environment. I've got 2 protons in my B environment, 2 protons in my C, 6 protons in D, and then 1 proton in my E. Okay, so we can start to see how this is getting all built together where we're using all of those different pieces of information to kind of put together that whole idea. Alrighty, so again, let me know if you got any questions and I will see you all later.